Einstein said that his greatest inspiration in physics was not the work of Isaac Newton, but the work of Maxwell. Uh, Maxwell's equations for electromagnetism represent the pinnacle of classical physics, the greatest achievement in classical physics. Classical meaning prior to the revolutions of quantum mechanics and Einstein's revolution in relativity. Uh, this pointed the way towards relativity and inspired Einstein to develop his own theory. But we haven't really noticed yet what made Maxwell's theory such a tremendous leap forward. He added this term to the equation, which seems kind of nice to restore this symmetry between E fields and B fields, but its true significance we're about to discover. We're going to see what remarkable discovery is hiding in plain sight here in Maxwell's equations. Okay, to do that, I'll have to show that Maxwell's equations can be written in these two different forms. We're familiar with the integral form of the equations. In the field of vector calculus, you can also write these equations in this form over here. So if you're familiar with divergence and curl, then you'll recognize the significance of these equations here. If you're not familiar with this mathematics, that's okay. Just know that this is a different way of writing Gauss's law, and this is a different way of writing Faraday's law using some different mathematics. Okay, the details aren't important right now. Okay, so here are Maxwell's equations written in integral form and differential form. Now let's take a brief detour and talk about oscillators and waves. A simple harmonic oscillator is a system that is capable of oscillating back and forth around some equilibrium point. So let's call this function f the displacement of our system from its equilibrium. So our system could be as simple as this little pink ball here moving up and down around this equilibrium point. So f is its displacement from the equilibrium, and f is a function of time as the ball moves up and down around this point. And so if our system undergoes simple harmonic motion, then it obeys an equation of this form. The second time derivative of the displacement from equilibrium f is equal to the opposite of some constant times that displacement. And we recognize that this constant is omega squared, where omega is the angular frequency for the oscillation that will occur here. Okay, so that's a single simple harmonic oscillator, one thing going back and forth. But if we put together a zillion simple harmonic oscillators, say imagining a stretched string, a taut string, sliced into little segments all next to each other, and if we imagine shaking one end of that string to sort of send ripples running down the string, then each little part of the string, each little segment, each little pink or white segment here could itself represent an individual simple harmonic oscillator. Each little segment could oscillate up and down. This little pink part right here could oscillate up and down as some wave pulse travels along the string. This little pink segment over here can travel up and down. So each little segment is an individual oscillator. Put all these oscillators together, and their collective motion, the way one oscillation triggers the neighboring oscillation, the collective action of all these neighboring oscillators can together comprise a wave. This wave-like pattern traveling to the right. And so if we have a wave traveling along this string to the right at some speed v, then this could be a snapshot of their string at one moment in time. And then sometime later, here could be another snapshot of our wave on the string. We see that our wave pulse has traveled to the right. So I've marked here the position of that highest peak, and I show that sometime later, that highest peak has traveled this distance, delta x. So that delta x would be related to the speed that our wave is traveling, at which our wave is traveling, and the amount of time that's passed between this moment and that moment. So f here is now our displacement of the string from equilibrium, but that displacement is different at every position along the string. So f is now a function of x as well as a function of time. F is a function of x and of t, instead of here where f is just a function of time because we have only one oscillator. Now we have many oscillators located at different x coordinates, so to specify some displacement, we have to say the time we're talking about, and we also have to say which oscillator are we talking about, which x coordinate. We're talking about this point here, or this point over here, or this point over here. Okay, so f is a function of x and of t. Now I just want to show you the structure for an equation that would describe a traveling wave like this. So if f is our function of position and time, giving the displacement from equilibrium of any one of these individual pink or white oscillators, then this equation here says that if the second time derivative of f is equal to a constant times the second, did I say that wrong? This is the second position derivative of f. If that is equal to some constant times the second time derivative of f, then our solution to this equation will be a wave traveling at a speed v that appears here. This constant is 1 over v squared. V will be the speed of that traveling wave. Okay, I just want you to look at the structure of this equation. And now let us return to Maxwell's equations here. In particular, Maxwell's equations in a vacuum. If there is no charges around, so the electric charge density is 0, and there are no currents flowing anywhere, so the current density is 0. So that's what we mean by in vacuum here. So there's no stuff around. Then the right-hand side of Gauss's law disappears, and that ampere term on the right-hand side over here disappears since there's no current, and we just have these equations here. And now the symmetry between them is even more apparent once we get rid of those source terms. Okay, so I'm going to just do a bit of vector calculus to put these equations together. If you're not familiar with vector calculus, that's okay, just stick around for the conclusion. So what I'd like to do is take the time derivative of this equation, take d dt of both sides. These are partial derivatives here since our functions b and e are functions of both position and time, so there's multivariable functions. So we take the time derivative of both sides of this equation. That gets us here. And now dB dt I'm going to replace with Faraday's law here. So dB dt can be replaced with the opposite of the curl of E. Put that in there, move a minus sign over, and use a vector identity to show that the curl of E is equal to this expression. Divergence of E is 0, so that drops out and simplifies down to this. This is the form of a wave equation. I've just done some algebra here to show that Maxwell's equations are equivalent to a wave equation. It's suggesting that the electric field can exhibit wave-like behavior. To be even clearer, if we reduce to just one dimension here, then this Laplacian here can be replaced with the second, this should be position derivative here, d squared x, or d squared e dx squared. Okay, making that displacement, we see that this has exactly the form of that wave equation I cited here. So we're showing that Maxwell's equations can exhibit wave-like behavior, or a disturbance in the electric field can travel as a wave. And then this constant that appears in front of our time derivative term, that constant we identify as 1 over v squared. So the waves, the disturbances in the electric field that travel along, will travel along at this speed, 1 over the square root of this combination of constants that is always stuck around in our Maxwell equations. Mu naught, the permeability of free space, epsilon naught, the permittivity of free space. We know the values of these constants. So let's put those values in, grab your calculator, calculate the result here, and 1 over the square root of this gives us a number that will represent the speed at which these waves travel. That value turns out to be about 3.0 times 10 to the 8th meters per second, which we recognize. That's a known speed to us. Apparently, the speed at which disturbances in the electric field travel is the same as the speed of light. We recognize this value as the speed of light. This here is Maxwell's tremendous leap forward. What he discovers by adding in his additional term to Ampere's law here, what he discovers is that electric and magnetic fields can exhibit wave-like behavior, and those waves travel at the speed that we know to be the speed of light. What Maxwell has discovered is that a traveling disturbance in the electromagnetic field is light. He discovered the nature of light. What Maxwell has done is not only show that electricity and magnetism are two aspects of a single common theory here. Electricity and magnetism are one. Maxwell has unified electromagnetism with optics. He has shown the nature of light, that light waves are ripples in electric and magnetic fields. So that includes radio waves, infrared, visible lights, ultraviolet lights, X-rays, gamma rays. The entire electromagnetic spectrum just represents ripples in electric and magnetic fields.